Construction began with environmental measures, sediment dredging, and seabed preparation. Prefabricated concrete caissons were floated from Marseille and placed on underwater fill. The caissons formed a protective belt around the site. A stone platform was then built using marine transport and conveyors to create Monaco's 6-hectare land extension. Step-by-step construction progress of the Yufelli dam body. Concrete pouring began on January 10, 2018. Workers used tower cranes and heavy machinery to transport and pour concrete layer by layer. As construction progressed, the dam body gradually rose, reaching 250 meters, surpassing the Dariner Dam. The timeline shows the systematic placement of concrete blocks and the movement of equipment across multiple levels. Cooling pipes are embedded to control the temperature of the concrete. Formwork systems are installed and repositioned for each new layer. To date, 3.765 million cubic meters of concrete have been poured. When completed, the dam will reach 275 meters with 4 million cubic meters of concrete. Concrete was poured continuously for 10 hours using 6 concrete pumps and over 100 concrete trucks. Workers placed and leveled the concrete in sections, using vibrators to eliminate air pockets and ensure proper compaction. As each area was poured, crews immediately began surface, finishing with bull floats and trowels. Coordination was crucial to maintain a steady supply and avoid delays. The pour covered the building's mat foundation, forming a strong structural base. The construction process of the IBS DIY begins with preparing the site for a dry construction system. Unlike traditional methods that require deep concrete foundations, this project uses a steel chassis as the base. The chassis is pre-engineered to support the structural load of the entire building. It is aligned and anchored into position, creating a stable and mobile foundation that reduces time and eliminates the need for wet trades. Following the chassis installation, the prefabricated steel structural components are delivered to the site. These include vertical columns, beams, and floor trusses. All parts are precisely fabricated off-site in a controlled environment by Superspan SDN BHD, ensuring consistent quality and accurate dimensions. On-site, the vertical columns are installed first and secured onto the chassis using bolts and brackets. Horizontal beams are then connected across the columns to form the skeletal framework of the structure. After the frame is in place, the floor system is assembled. Prefabricated floor trusses are positioned between the beams, followed by the installation of lightweight floor panels on top. These panels are pre-cut to size, allowing for quick placement with minimal adjustment. This step creates a strong and stable floor without using concrete slabs, maintaining the dry construction approach. Next, wall installation begins. Prefabricated wall panels arrive with insulation and cladding already integrated. Each panel is lifted and bolted directly to the steel framework. The wall panels are designed for rapid alignment, and their modular structure ensures tight joins that enhance both strength and energy efficiency. The use of these panels significantly reduces construction time and on-site labor. Once the walls are secured, roof trusses are assembled on top of the frame. Lightweight metal roof sheets or insulated sandwich panels are then fastened to these trusses. The roofing system is designed for quick installation and immediate weather protection. With the roof completed, the structure becomes fully enclosed, allowing interior work to begin regardless of external weather conditions. The next stage involves installing internal partitions. These are also prefabricated and easily attached to the steel frame. The layout can be adjusted depending on the desired room configuration. Once the partitions are fixed, utility systems are integrated. Electrical wiring and plumbing pipes are installed within the frame and wall cavities. Since the components are designed with service integration in mind, the process is fast and organized. After utilities are installed, interior finishes begin. Drywall panels are mounted onto interior walls, followed by ceiling boards and floor finishes. As most surfaces are prepared off-site, minimal adjustments are required on-site. This reduces defects and speeds up the finishing phase. Paint or interior cladding is applied to complete the walls and ceilings. Doors and windows are fitted into pre-cut openings in the wall panels. The frames and sashes are aligned and sealed to prevent air or water infiltration. Since the panel openings are factory cut, the fitting process is quick and accurate. Fixtures such as lights, sockets, and plumbing hardware are then installed and connected to their respective systems. Exterior finishing includes sealing joints, applying trim, and adding protective coatings if needed. The structure is then checked for alignment, insulation performance, and stability. A final inspection ensures that all systems are functional and meet safety standards. Finally, the house is painted, with workers applying finishing touches from the inside out. Throughout the process, no heavy machinery is required on site. The components are light enough to be manually handled or moved with small equipment. This makes the system ideal for remote areas or locations with limited access. Moreover, the dry construction technique ensures less dependence on weather conditions, enabling uninterrupted progress. From start to finish, the construction of the IBS DIY house takes approximately 12 days. The entire process from site preparation and steel frame assembly to wall and roof installation, utilities, and interior finishing is efficient, modular, and environmentally responsible. The system combines speed, quality, and simplicity, showcasing the practical advantages of modern prefabricated housing in Malaysia. The application of asphalt rubber SAMI on the Pantura National Road in Susukan, Pamanukan. First, a distributor truck sprays hot asphalt rubber evenly onto the existing road surface. Immediately after, a chip spreader follows to apply aggregate stones over the asphalt rubber layer. Workers ensure proper distribution and coverage. Then, pneumatic rollers compact the aggregate to embed it firmly into the binder. This process creates a waterproof interlayer that prevents reflective cracking and improves road durability by resisting rutting, aging, and fatigue. The surface is left to cure before opening to traffic. The construction process of tilt-up concrete walls begins with the preparation and installation of tilt-up formwork directly on the floor slab. These formworks are carefully positioned to define the dimensions, openings, and embedded elements of each wall panel. Reinforcement steel is placed inside the forms, along with inserts for lifting and bracing. Next, concrete is poured into the horizontal forms to create the wall panels. The concrete is vibrated to eliminate air pockets and ensure uniform compaction. Once the concrete reaches the required strength, formwork is stripped, and the cured panels are prepared for lifting. A metal structure, including steel columns and beams, is then partially erected to provide alignment references. Using cranes and proper rigging equipment, each concrete panel is lifted into a vertical position and carefully placed onto pre-marked foundation lines. The panels are temporarily braced to maintain position until final connections are secured. After wall erection, the metal structure is fully assembled and bolted into place. The roofing system is installed using KR18 metal sheets, which are roll-formed and joined using concealed fasteners for weathertight sealing. Painting is applied to wall surfaces for aesthetic and protective purposes. Subsequently, earthworks are carried out to grade and level the site. Finally, asphalt is laid to form driveways and access roads, completing the project. At the beginning of a paving operation, the crew must address key setup tasks following the tailgate meeting. A comprehensive pre-paving checklist is executed to ensure the machine is properly configured. This includes heating the screed to the correct operating temperature, which is critical for material flow and compaction quality. The toe points are centered to maintain consistent screed elevation and mat thickness across the entire width. Next, operators set the paving width using the screed extensions and configure the main screed crown to establish the desired cross slope. Screed slope extensions are then adjusted for transitions and edge matching. The screed is lowered into its starting position, typically on a starting board or previously paved surface, to ensure a smooth start. The end gates are positioned to define the mat boundaries. The auger height is set approximately 2 inches above the target lift thickness, allowing proper distribution without dragging or segregation. Feed sensors are calibrated to control material delivery to the augers based on head of material height. The auger chamber is filled, ensuring an even distribution of mix across the width before motion begins. Before paving, a tack coat is applied to the prepared base surface. It acts as a bonding agent between pavement layers. The surface must be clean, and the tack must break, meaning water in the emulsion evaporates, turning it from brown to black before hot mix asphalt is placed. Once ready, the truck is directed into position. The hopper should remain between 1/3 and 2/3 full to ensure consistent material flow. The conveyor system moves the mix from the hopper to the augers. Material flow is regulated by variable speed controls or flow gates. The augers distribute the mix uniformly in front of the screed. A constant head of material is maintained to ensure smooth and even paving. The screed spreads and pre-compacts the mix, maintaining the angle of attack to control mat thickness and surface texture. Compaction follows immediately. A steel drum roller performs initial breakdown rolling. A pneumatic roller follows for intermediate and finishing passes to achieve the required density and surface quality. The canal paver machine begins operation by moving along the prepared canal bed. A concrete mix is discharged in front of the machine, where a rotating auger spreads it evenly to the required level. Next, a vibratory cylinder compacts and finishes the concrete surface, ensuring a smooth and uniform layer. The machine advances slowly on rails, maintaining precise alignment. It is capable of paving both the canal bed and side slopes as needed. A PVC inserter, if equipped, installs PVC strips either vertically or longitudinally during the paving process. For expansion joints, a groove cutter may operate simultaneously. The modular frame design allows for quick assembly and adjustment of paving width, and the entire system delivers high productivity with consistent finish quality. The construction of Glenouth Wind Farm began with the development of 9 kilometers of internal access roads, designed to withstand heavy loads and ensure year-round access. These roads required significant earthworks, including excavation, grading, and the installation of geotextile membranes for soil stabilization. In boggy or soft ground areas, stone platforms and drainage systems were incorporated to ensure long-term. Next, excavation of turbine foundations was carried out. Each base required the removal of approximately 500 to 600 cubic meters of soil to reach stable subsoil. Reinforcement cages were pre-assembled and installed, followed by the pouring of high-strength concrete to form the turbine foundation plinths. Anchor bolt cages were positioned precisely using jigs to ensure alignment with the turbine toe. Transport of turbine components posed a major logistical challenge. Large dimension loads, such as rotor blades and tower segments, were delivered via customized trailers. This required public road modifications, including widening curves, reinforcing verges, and temporarily removing obstructions like signposts and barriers. Temporary traffic management was implemented during these convoys. Erection of the turbines involved using heavy lift cranes, typically with lifting capacities exceeding 500 tons. Tower sections were assembled sequentially, followed by the nacelle installation. Rotor blades were either installed individually or pre-assembled into a rotor star and lifted in one piece, D. Electrical infrastructure included laying approximately 7 kilometers of medium-voltage MV cables between turbines and a newly constructed 38 kilovolts on-site substation. An additional 20 kilometers of underground cable connected the substation to the national grid. All civil works were executed in parallel, with strict environmental management practices, including sediment. The machine lifts the track, removes dirty ballast, screens and recycles clean stones, then returns and levels them beneath the sleepers. The builders begin by stacking ICF blocks on top of the poured footings, utilizing the even interval height steps to lock each piece securely. For the circular tower section, they use build block radius blocks to form the curved wall. Horizontal rebar is inserted during stacking according to the engineering plan. After all blocks for the basement walls are stacked, they brace the structure and install scaffolding. Using the scaffolding, they place vertical rebar reinforcement between the courses, with horizontal rebar alternating inside and outside. To prepare for the build deck installation, the builders cut the top course using a table saw and sawzall, carefully notching only the top web to maintain structural integrity. The basement walls reach a height of 7 full courses, with the 8th course trimmed down to 4 inches. This allows the build deck to sit directly on top, completing the wall height of 9 feet 4 inches before the deck is poured. A telescoping drill with a bullet tooth auger breaks ground at the pier location. Slurry made of minerals, polymer, and water is added to stabilize the shaft walls. Drilling continues as dirt and excess slurry are removed. After reaching the base, a rebar cage is inserted for reinforcement. Concrete is then pumped into the bottom of the shaft using a tremie while the slurry is displaced. This completes the wet shaft and slurry pier process, used when standard methods fail due to underground or collapsing shafts. The drilling process begins with the Bauer rotary drilling rig being positioned precisely at the marked location. Workers then guide the drill casing vertically to ensure alignment. Once set, the rotary drive starts operating, rotating the drilling tool and driving it into the soil. As the tool penetrates deeper, spoil is brought up and removed from the hole. The rig continues drilling in stages, pausing periodically to extract excavated soil using a clamshell or auger tool. Steel casing is added segment by segment to maintain borehole stability, particularly in loose soil layers. These casings are screwed or pressed into the ground using the rotary drive. Drilling progresses until the designed depth is achieved. Throughout the process, workers monitor alignment and depth using measurement devices mounted on the rig. Once the final depth is reached, the drilling tool is withdrawn and workers prepare for reinforcement cage installation. The prefabricated steel rebar cage is lifted using a crane and slowly lowered into the borehole, ensuring it remains centered. Guide frames or spacers are used to maintain cage position inside the casing. Finally, concrete is poured using the tremie method. A tremie pipe is inserted to the bottom of the hole and gradually lifted as concrete is pumped, displacing any remaining drilling fluid or loose soil. This ensures continuous and clean concrete placement. After concreting is complete, the temporary casing is withdrawn, completing the pile construction. The CAT 320D excavator digs a trench by lowering its bucket into the ground, pulling soil toward the machine and lifting it out. The operator precisely controls the arm and boom to shape the trench. Excavated soil is placed beside the trench for later removal or backfilling. Builders used 16 hydraulic hoists to lift 3,000 tons of steel to 250 meters in 3 batches. Facing strong crosswinds, they worked within a short weather window. After 20 days and nights, they completed the 300-meter-long crystal corridor, creating the world's largest horizontal skyscraper. The process begins with rebar cutting and bending to shape the steel reinforcement according to the T-wall design. After preparing the rebar, the molds are readied by applying molding oil to ensure easy removal later. Next, the reinforced steel bars are carefully positioned inside the molds. Before pouring concrete, a toolbox meeting is held to confirm readiness and safety procedures. Concrete with a strength grade of FC50 is prepared and tested with a slump flow test to verify its quality and consistency. Concrete is then carefully poured into the molds using buckets fed from mixer trucks. During pouring, vibration tools are used to compact the concrete, ensuring it fills all spaces without air pockets. Once the concrete has set, the molds are removed in the demolding phase. The precast T-wall segments are then handled using cranes and moved to the finishing area. Here, the products are arranged according to layout plans, and finishing touches including labeling are applied before the segments are ready for use. Throughout the entire process, supervisors monitor quality to maintain high production standards. The production process begins with the concrete being loaded into the mold mounted on the CGM vibrating demolding machine. High-frequency vibration is applied to compact the dry-cast concrete inside the mold. Once compaction is complete, the mold is lowered to the floor. The machine then rotates the mold 180 degrees, allowing the concrete box culvert to be gently demolded directly onto the ground. After demolding, the machine lifts the empty mold and returns to its starting position, ready for the next cycle. Throughout the process, no external handling equipment is used, and the box culvert remains on the production surface to cure. The molds are fully interchangeable and can be customized according to production needs. This method enables efficient, continuous manufacturing of reinforced or non-reinforced concrete box culverts with high dimensional accuracy and surface quality. Determine site, compact fill, build base, lift roof with air pressure, weld, install nickel shell, test with water. The construction of the bridge substructure begins with careful excavation of the soil at the designated site. Excavators and heavy machinery are used to remove earth and reach the planned foundation level, ensuring a stable base for the bridge abutment. The excavation process follows precise measurements and design specifications to avoid over-excavation or insufficient depth, which could affect the structural stability. After completing the excavation, workers prepare for the footing construction by installing formwork. The formwork is carefully assembled to define the exact shape and dimensions of the footing, which is the structural element transferring loads from the bridge to the ground. Before placing the concrete, steel reinforcement bars or rebar are arranged inside the formwork. These rebars are tied together to form a cage that provides tensile strength to the footing, preventing cracking under load. The positioning and spacing of the reinforcement are checked thoroughly to meet engineering standards. Once the reinforcement and formwork are confirmed, concrete pouring begins. Ready-mixed concrete is transported to the site and poured steadily into the formwork. Workers use internal vibrators to consolidate the concrete, removing any trapped air pockets and ensuring the concrete fully envelops the rebar cage. This compaction is essential for achieving maximum strength and durability of the footing. After the concrete is poured, the surface is leveled and smoothed using hand tools. The curing process follows, where the concrete is allowed to harden and gain strength over several days under controlled conditions. During this time, formwork remains in place to support the concrete until it achieves sufficient load-bearing capacity. Throughout the entire process, strict safety protocols and quality inspections are observed to ensure the footing construction meets design requirements and structural integrity. This completes the foundation stage of the bridge substructure, setting a solid base for subsequent construction phases.